To understand how the Yellowstone ecosystem works, to really understand the mechanics of the ecosystem, we're going to have to go into some basic chemistry. This will eventually help us better understand the metabolism of the plants and animals in the ecosystem, and also, some of the environmental contaminants and pollutants and the effects that they can have. So as we look at chemistry, what chemistry is, chemistry studies the properties and interactions of elementary particles of matter and the atoms and molecules they form. So that brings up the question then, well, what is matter? Well, matter is anything that has mass and takes up space or has a volume to it. And when we look at the states of matter, which we will be considering at different times, there are 4 states of matter. We're really going to be concerned with the first 3 of these. So states of matter include solids. So in a solid state, the atoms and molecules are in a fixed position. They may be vibrating, but they don't move around. And then we have liquids and gases. And in liquids and gases, molecules and atoms are colliding and moving around. But what distinguishes a liquid from a gas is basically the amount of space between the particles as they move. And then we're really not going to get into plasma, but plasma is the 4th state of matter. Superheated matter, basically the particles of atoms and molecules, electrons are stripped away from the nucleus and the particles are separated. And it's an electrically neutral substance, but it's not something that we're really going to be discussing in this particular class. Okay, so when we talk about matter or chemistry, we're really talking about elements, and elements are composed of so-called pure substances. Pure substances are composed of like atoms, and examples would be things like hydrogen and oxygen, carbon, nitrogen, and others that we'll certainly be talking about regularly in this class. So in looking at the structure of an atom then, when we consider the structure of an atom, it begins with the nucleus. We have the nucleus of the atom, and the nucleus of the atom is composed of relatively large subatomic particles, which is a little bit of an oxymoron, I guess. But protons have a mass of approximately 1 Dalton, or 1 atomic metric unit. And also in the nucleus we'll find neutrons. And neutrons also have about a mass of 1 Dalton. One of the differences in the particles is that protons do carry a positive charge, whereas neutrons have a neutral charge. They do not have an electromagnetic charge. And then surrounding the nucleus, and we'll kind of represent these in what we call orbitals or shells, but around the nucleus we have electrons, and electrons have a very, very tiny mass, an insignificant mass as far as we're concerned, 1/1800th of a Dalton, or atomic metric unit, and they carry a negative charge. So as we're going to see, in some atoms we'll have a balance between protons and electrons, which will give them a neutral charge. Others will see an imbalance in these charges, and then those particles will take on a net positive or negative charge. Also, when we look at, again, the basic structure of the atom, again, we're going to be representing electrons as existing in discrete locations, but the reality is that electrons can be in a cloud-like distribution, although we're going to be representing them in discrete orbitals, circular orbitals. That's not necessarily a really realistic representation. Also, when we look at the nucleus is held together by a force similar to gravity. It's called strong force. And then electrons are held in place partly by the difference in the electromagnetic attraction, but also by another force, which is called weak force. Now, when we look at atoms of the different elements, they're arranged in a periodic table, and each element has its own little box. And so as we look at the components in the box in each element then, as you can see, this would be for the element chlorine. So in the case of chlorine, we have this number 17. It's telling us it's element number 17, and that is the atomic number. And the atomic number tells us the number of protons in that particular atom. We also have the atomic symbol for chlorine, and then also the atomic mass. And so the mass is telling us the approximate mass of the atom, but really atoms are so small, really what that represents is the mass of a mole of atoms. And so a mole is the standard unit of chemistry, because again, we're talking about particles that are so small. So the word mole just represents a number, just like the word dozen represents the number 12, and the phrase baker's dozen represents the number 13. A mole is just a really big number, so-called Avogadro's number, 6.02 times 10 to the 23rd particles. So anyway, I will be talking about atoms, but chemists really talk about moles of atoms. Now, another thing to understand about these numbers in is that, again, the atomic number is telling us the number of protons in the nucleus. That's what distinguishes one atom from another, is the number of protons in the nucleus. And the atomic mass, because the number of the atomic masses of protons and neutrons are approximately 1 each, the atomic mass of the atom is also telling us the approximate number of particles in that atom. So we can use this information then to determine the structure of the nucleus of an atom. So the atomic number, again, tells us the number of protons in the nucleus. The atomic mass is telling us not only the mass of a mole of particles, but it's also giving us an approximate number of particles in the nucleus, the number of protons plus neutrons. So if we want to determine the number of neutrons, then we would just subtract the atomic mass from the atomic number. So again, we'll take the atomic mass and subtract the atomic number, and that will give us the number of neutrons in a particular atom's nucleus. All right, so again, if we look at this example from chlorine, then if we go ahead and round off 35.45 to a whole number, use that as 35, that would be telling us there are 35 protons and neutrons in the nucleus. 17 is telling us the number of protons. Subtract that, and that would give us 18 neutrons in that particular nucleus. So looking at some other elements then, again, if you look at hydrogen, hydrogen has, I need to go back. Hydrogen has a mass of 1, and it has an atomic number of 1. So if you subtract 1 from 1, that would tell us then that in that particular nucleus there are 0 neutrons, and we'd know there was 1 proton because the atomic number tells us the number of protons. So again, what distinguishes any element from a number is any other is the number of protons in the nucleus. If we look at potassium, another example, atomic mass of 39, so there are 39 protons and neutrons. The atomic number is telling us 19 of those are protons, so if you subtract 19 from 39, it tells us there are 20 neutrons. And then copper, atomic mass of 64, atomic number of 29, so there's 64 protons and neutrons, 29 of those are protons. Subtract, and it will tell you that there are 35 neutrons in that particular nucleus. So the reason that becomes significant is that when we look at atoms in nature, they can have variable numbers of neutrons, and we refer to those as isotopes. So as we look at this chart, you'll notice that there are 3 versions of hydrogen. There's hydrogen 1, and there's hydrogen 2, and hydrogen 3. And they differ by the mass. They have different masses, but what they have in common is that they all have the same atomic number, so they all have 1 atom in the nucleus, but they have variable number of neutrons in the nucleus. So they're all hydrogen because they have 1 proton, and that means they all have the same atomic number, and they will have similar chemical characteristics. So what is a characteristic of some isotopes is that some isotopes are radioactive. And I'll talk about that in a second, and you can't really tell that from the periodic table, but basically radioactive isotopes, cannot hold their structure. They will lose energy or they will lose particles, and radioactivity can be harmful to organisms. And then another example, you can see that there are 3 different isotopes of carbon. There's carbon-12, carbon-13, carbon-14, and again, they're all carbon because they have an atomic number of 6, which means they have 6 protons, but they have variable number of neutrons. And carbon-12 is a stable isotope, whereas carbon-13 and carbon-14 are radioactive isotopes. Okay, now when it comes to the chemistry, though, it's really all about the electrons and distribution of electrons. And so electrons will be, the way we're going to represent them at least, we're going to show them as being distributed in shells around the nucleus. And we normally start with the assumption that there will be the same number of electrons as protons, although we'll find out that doesn't always hold up. And another characteristic of these shells is that each shell will only hold so many electrons. So you can see that in this chart that shell number 1 will hold a maximum of 2 electrons. Shell number 2 will hold a maximum of 8 electrons. Shell number 3 holds a maximum of 18, and so on. And the shells actually have complex 3-dimensional shapes, but that's beyond my ability to represent them, and we don't really need that kind of knowledge for this class. So we're going to keep this representation fairly simplistic. And the way that we determine the number of electrons that a particular shell can hold is that we use this formula 2n squared, where n represents the electron shell number. So again, if you were trying to determine the maximum number of electrons, shell number 1 will hold a maximum of 2. Shell number 2 will hold a maximum of 8 according to that formula. Shell number 3 holds a maximum of 18, but there are some complexities as we get into these outer shells. For example, shell 3 has an inner subshell of 8, an outer subshell of 10, and so that inner subshell has to fill first, and then we move into the outer shells. Shell 4 holds a maximum of 32, but that's composed of subshells of 8 also, 4 subshells of 8. So again, I would just expect you to be able to know the maximum number in each shell and not necessarily know which ones have subshells and so on, but it does get a little more complex as we move out. So again, when we look at chemistry, chemical bonds, and so on, really what we're talking about here is distribution of electrons. So one of the things I want you to know about atoms is this, that if a shell or if a subshell is full, then an atom is not likely to react chemically with another atom. If the shell or subshell is not full, then they will chemically react with other atoms. And what this amounts to when I say chemically react, what they're going to be doing then is either transferring or sharing electrons to fill shells. So what's most important to an atom is that they have full shells. It's not that they're electrically balanced. Charge is not that important. What's important is having full shells. So if we look at these two atoms here, hydrogen and sodium, you'll notice that hydrogen only has 1 electron in its outer shell, and sodium only has 1 electron in its outermost shell. So those shells are not full. So they are going to react with other elements. And you'll also notice that if you look at the periodic table, both hydrogen and sodium are found in the first column. So all of the elements in this first column of the periodic table then have 1 electron in their outermost shell, and they will behave similar chemically. Calcium and magnesium, as you see, have 2 electrons in their outermost shells. So these are 2 atoms, again, which do not have full shells. These would be chemically reactive. And if we looked at the periodic table, you'd happen to see that magnesium and calcium are in this column 2A, and they, as it turns out, have similar chemical properties as well. So this is one of the characteristics of the periodic table. We have these chemical families where different groups of atoms are arranged vertically according to the number of electrons in the outermost shell, and then they will have similar chemical properties. Another example, fluorine and chlorine. Again, they have 7 electrons in the outermost shell, and these electron shells are not full, so they would be chemically reactive. And guess what? They would be in the same chemical family, which would be column 7 over here, although my cursor isn't showing up. And last but not least, the neon and argon have 8 electrons in their shell. This fills the shell here. It fills the subshell here. So those would not be chemically reactive and also would be in the same chemical family. So they also share similar chemical properties. So again, if a shell is not full, chemically reactive, shells full will not be chemically reactive. And we call this outermost shell, the one that is potentially reactive, the valence shell, and that really determines, whether an atom will bond or not. So as we look at chemical bonds, then there are 2 types of chemical bonds, ionic bonds and covalent bonds. Ionic bonds involve a transfer, a one-way transfer of electrons from one atom to another. Covalent bonds involve a sharing of electrons. So an example of an ionic bond occurs between sodium and chlorine. Sodium has 1 electron in its valence shell, chlorine has 7. This creates kind of a dilemma. So sodium could either gain 7 to fill the shell or lose the 1. Chlorine could either gain 1 to fill the subshell or lose the 7. You can probably intuitively feel that it would be easier for sodium to give its electron to chlorine, and that would make everybody happy. And that's what's going to happen if these come together in the right way. So at the end of this transfer of electrons in, we end up with full outer shells, but we also then have an imbalance in charge rather. So there would be 11 protons here, only 10 electrons. So sodium takes on a positive charge, and we have 18 negative charges here, 17 positive charges. Actually, and so chlorine takes on a negative charge. So by gaining the electron, it takes on a negative charge, and the fact that they each now carry an electromagnetic charge, that's what holds them together. So positively charged particles we call cations, negatively charged particles we call anions. So this ionic bond produces ions, and that's what an ionic bond is all about. Ionically and so again, this shows us how the sodium and chlorines would be held together, and they actually form crystals. So ionic bonds then tend to form between metals and metalloids and nonmetals. So as we look at the periodic table, there's a line here that basically separates the metals and nonmetals, or excuse me, metals and metalloids from the nonmetals. So members from this side tend to bond with this group in forming ionic bonds. They tend to form between atoms with very different electronegativities. That's something I'll come back to in a few minutes, but electronegativity refers to how strongly an atom holds electrons. High electronegativities mean that they're selfish, they hold on to electrons strongly. Weak electronegativity means that you don't hold on to an electron strongly. So if we have very different electronegativities, one selfish atom, one not so selfish, then the selfish atom steals electrons from the non-selfish atom. They tend to form hard brittle compounds with high melting points, and they readily dissolve in water, forming free ions. So if you're going to take salt, put it in water, the individual sodiums and chlorines separate and dissolve in the water. The other kind of bond is a covalent bond, and in covalent bonds what happens is that atoms share electrons. So if we have oxygen and two hydrogens, they have the potential to form covalent bonds. And so in covalent bonds what happens is that in this case the oxygen would share one of its electrons with each hydrogen. So each hydrogen then would be getting an electron from the hydrogen. And each hydrogen would share one of its electrons with the oxygen. So by sharing electrons, it gives the illusion that they all have full shells. In other words, each hydrogen will have one of its electrons and one from oxygen, so it has two electrons available to it, so it thinks it has a full shell. And then the oxygen has not only its 6 electrons, but it's borrowing one from each hydrogen at certain times, so it has 8 electrons available to it, and it thinks its shell is full. So by sharing electrons in this way, they think they have full shells. Now, what's interesting about the sharing in water, however, is that oxygen tends to be more selfish. It's more has a higher electronegativity than hydrogen. So at any given time, oxygen is more likely to have more than its complement of electrons than the hydrogens are. So as a result, the molecule will be slightly positive on one end and slightly negative on the hydrogen, slightly negative on the oxygen end and slightly positive on the hydrogen end. And so this is like the poles of a magnet, and so we refer to this as a polar molecule. So these areas of positive and negative charge then cause interactions between adjacent molecules, and this is kind of an important characteristic of polar molecules. So they not only have a particular structure themselves, but they influence other molecules. And then some covalent bonds will be nonpolar. So methane is an example of this, a carbon with 4 hydrogens. When they share electrons evenly with one another. So there's no net regions of positive charge and there are no net regions of negative charge. So we refer to these as nonpolar covalent bonds. So again, as we'll get to this later, but when we look at diagrams that are represented by covalent bonds, we normally just use a line to represent the covalent bond. And each line represents a sharing of a pair of electrons. So in these cases, for example, carbon would be sharing 1 electron with hydrogen, and hydrogen would share 1 electron with each carbon. Okay, so again, covalent bonds then tend to form between nonmetals with similar or moderately different electronegativities. And so again, as we look at the periodic table, our nonmetals will be over here on the right side. And again, continuing the list, sharing may be unequal, forming polar molecules. Covalent bonds are stronger chemical bonds than ionic bonds. And when soluble in water, the entire molecule tends to dissolve in the water as opposed to coming apart the way ionic bonds do. So this purple molecule is surrounded by water molecules. That's the covalently bonded molecule. So when it comes to bonding, here are really the things I want you to know about it then. There are 2 things we have to look at. First is compatibility. If you look at the valence shells, they need to be compatible in the sense that one atom needs to lose electrons in a certain number, and the other atom needs to gain electrons in a way that will fill outer shells. So when we look at whether atoms will bond with one another, they need to be compatible. So you look at the valence shells and determine whether one needs a certain number of electrons and the other can give away a certain number of electrons, and then that, or share electrons in a way that will fill shells. So they have to be compatible in terms of filling shells. And then the other thing that can affect the type of bond that forms is electronegativity. So again, electronegativity is a measure of an atom's affinity for an electron. The higher the electronegativity, the more strongly it bonds electrons, and the less likely it is to give away that electron. So looking at electronegativity then can affect whether we have polar covalent, nonpolar covalent, or ionic bonds. So what I'd like you to do is to take a look at a little demonstration that we prepared for our Biology 101 class, and it explains the difference between the ionic, polar covalent, and nonpolar covalent bonds. Kayla and I are going to demonstrate the difference between a polar covalent bond, nonpolar covalent bond, and ionic bond, and the role of electronegativities in what type of bond will form. And so the analogy here is that we're going to be like two children playing. And so we're going to be, sharing tennis balls with one another, and also representing atoms sharing electrons. So initially, what we're going to start off with is we're going to say that we have similar temperaments. So let's say that we're both very sharing. And this, again, in terms of bonding, would mean that we have similar electronegativities. So if we have similar temperaments, similar electronegativities, and keeping in mind that electronegativity is kind of the selfishness of an atom. So neither one of us is particularly selfish related to electrons, and let's see what would happen then. So we're going to share. And you'll notice that we're sharing nicely. So that if at any given time we were to stop, we would each have an equal number of tennis balls, in this case an equal number of electrons. So there's no net charge to our molecule. So this would be what you would find in a nonpolar covalent bond. So we're sharing, that makes it covalent. There's no region of positive or negative, that makes it nonpolar. So again, that occurs when you have similar atomic temperaments or similar electronegativities. Okay, now let's see what would happen if I'm a little more selfish. What if I have a slightly stronger electronegativity compared to Kayla? So that means then I have to think about it a little bit, but I'll still share. So it's still a covalent bond because we are sharing still. But if you were to stop time at any given moment, I'm more likely to have the electrons, or I'm likely to have more electrons than her. That will make my end of the molecule slightly negative compared to hers. So this would be a polar covalent bond. Okay, last but not least, what if I'm a much more selfish kid than her? So instead of a moderate difference in temperaments or electronegativities, what if there's a big difference? She has low electronegativity, I have high, or she's not very selfish, I'm very selfish. So now when we try to play, I just take it and I keep the ball. Or in this case, I'm keeping the electrons. So now it's not a sharing anymore, it's a transfer. I'm stealing it, I'm taking it. So now I permanently take on a negative charge, I'm an anion. She now has permanently a positive charge since she's lost an electron, so she's a cation, and that electromagnetic attraction is what keeps us together. So that then is the difference between a nonpolar covalent, a polar covalent, and an ionic bond. So hopefully you have a feel then for what a chemical bond is and why these different bonds form. So, and again, I want to emphasize then that chemical bonding is not random. Okay, it's not random. It depends on the compatibility and electronegativities as to whether a bond will form and then whether an ionic or covalent bond will form. Okay, now following up on that then, when we look at bonding of different elements, we can refer to that as compounds. So a compound would be two or more atoms of different elements chemically bonded together. And some examples, sodium chloride would be an example of a compound. Glucose, we see carbon, hydrogen, oxygen. Those are different elements, so that would be a compound. Carbon dioxide, carbon, oxygen, that certainly would be a compound. And something like oxygen gas, O2, we would not describe as a compound, but it is a molecule. So when we have two or more atoms bonded together with covalent bonds, we refer to that as a molecule. So not all molecules are compounds. And then very briefly, I also want to quickly go through chemical reactions. So a chemical reaction then is a chemical rearrangement. And when we look at chemical reactions, we have on one side of an arrow reactants, on the other side we're going to have products, and the arrow is called a yield sign, and that's telling us that we actually have a reaction occurring. So I wouldn't expect you to be able to write reactions, but I want you chemical equations, and again, the chemical equation represents a chemical reaction. But I would expect you to be able to recognize that it is written correctly. So in this particular example, again, what we have on the reactant side is 1 glucose molecule, 6 oxygen molecules that give rise to 6 carbon dioxides and 6 water molecules. And so again, if there's a number out in front, that tells us the number of each molecule. So again, there's only 1 glucose, there's 6 oxygens, there's 6 carbon dioxides, there's 6 waters. And then the subscripts tell us how many of each particular atom there are in that molecule. So in the case of glucose, we've got 6 carbons, we've got 12 hydrogens, we've got 6 oxygens. Here we've got 2 oxygens, here we've got 2 oxygens, here we've got 2 hydrogens. So if we look at a chemical equation, it's really like a recipe, if you will. Under certain conditions, if we have a certain number of reactants, it will give us a certain type of product. So if we were to look at the elements on one side, we should have the same elements on the other side. If we look at the numbers of each atom, they should match on the reactant and product side if it's written correctly. Because in chemical reactions, atoms are neither created nor destroyed. They just rearrange themselves. So again, if we look at the reactant side, then we would have a total of 6 carbons. We would have a total of 12 hydrogens. And we would also have a total of 12 oxygens, because again, we've got 6 O2s. So that's a total of 12 oxygens here. And then if we look at the reactant side, or excuse me, the product side, again, we would expect to have the same outcome, and we do in this case. So we end up with 6 carbons. We end up with our 12 hydrogens. And again, we have 12 hydrogens because we have H2 here. It's H2O, but we have 6 of the H2Os. So that's a total of 12 hydrogens. And then also 18 oxygens in this case. And I may have said 12 before, but we have a total of 18 oxygens. We have 6 times 2 here, plus our 6 here is 18. And on the reactant side, we had our 6 times 2 is 12 here, plus our 6 here for a total of 18. So I think I may have had that wrong to begin with. So again, fortunately here we have our equation written properly. We start with a certain number of atoms on our reactant side. We end up with the same number of atoms on our product side. And so this is a properly written equation. All right, so that's it for chemistry today. I'll see you next time.